How are y'all doing this morning?
Doing great.
Anybody have any questions regarding the homeworks or anything? All right, well then let's jump into our in-class assignment. So let me share. All right. This first bit is just effectively applying the techniques of source transformation, right? Where source transformation is we can replace any practical voltage source with an electrically equivalent practical current source, and vice versa. We can replace any practical current source with an electrically equivalent practical voltage source. So for part A here, we have a practical voltage source because it contains an ideal voltage source, an independent voltage source in series with a resistor. So the electrical equivalent for that will be a practical current source. Let me change my color here. In parallel with a resistor. So the resistor values are always going to stay the same. So this is going to be a current source. Is the direction going to be up or down?
Up.
Up. Right. So the head of the arrow will be in the same location as the positive polarity terminal. Since positive polarity terminal is on top, the head of the arrow should be directed up. What value should my practical current source have for the current source portion?
10 volts divided by 5 kilo ohms.
Right, so 10 volts divided by 5 kilo ohms is 2 milliamps. And there we go. It's as simple as that. For part B, we have a practical current source. So that means that we should have an electrically equivalent practical voltage source. The resistance value stays the same. So should the positive polarity terminal of my voltage source be on top or bottom here?
Bottom.
Bottom. All right. And what value should my voltage source have?
16 volts.
16 volts. Does it matter at all that I put my 8 ohm resistor here connected to the negative polarity terminal, or if I put it over here where it was connected to the positive polarity terminal?
No, it shouldn't.
Right, it shouldn't, because these two elements are in series, so the order in which we put them is completely irrelevant. So it will give you the exact same results as if the 8 ohm resistor was in either location. All right, for part C, we have a practical voltage source. So we're going to find the electrical equivalent practical current source. Since the positive polarity terminal is on bottom, it will be direction down, and 3 volts divided by 6 ohms is 1/2 of an amp. Alrighty, and finally for part D, we have another practical current source. So the electrical equivalent would be a voltage source. 2 ohms, and 2 ohms times 7 amps gives us 14 volts. Positive polarity terminal should be on top because the arrow is directed up. So this one was really easy, in my opinion. Any questions?
No, sir.
All right. Now let's get on to something a bit more difficult here. So problem 2 asks us to calculate the maximum amount of power that can be delivered to a well-chosen load resistor RL. So what we're going to have to do is we're going to have to make this, everything that I've circled, look like either a practical voltage source or a practical current source in order to apply the maximum power transfer theorem. So I'm going to redraw this real quick with open terminals where RL would be. Microamperes. So we have a practical current source here, and we have a practical voltage source here. So do any of you guys have any idea what steps we should take?
You can multiply the 27 microamps times the 750 kilo ohm to have a voltage source with positive polarity up.
Alrighty, so if we take that gentleman's suggestion, so let's see, 27 microamps times 750 kilo ohms gives me a voltage source 20.25 volts in series with a 750 kilo ohm resistor in series with a 3.5 mega ohm source, or a mega ohm resistor, 1.2 mega ohms. All right. What can we do next?
I put the resistors in series and then I changed it back into a current source.
Okay, so
at the same time I changed that voltage source to a current source also.
Okay, so let's go through this step by step. You definitely have the right idea here. So 3.5 mega ohms plus 750 kilo ohms should be 4.25 mega ohms, right? So converting that original practical current source into a practical voltage source allowed us to combine those resistors. I believe your suggestion was then to convert this practical voltage source back into a practical current source. And I believe you also said that you converted this practical voltage source into a practical current source as well. So let's take care of both of those steps. So we are going to have, I might need to give myself a little bit more room here. 20.25 volts divided by 4.25 mega ohms gives me a 4.765 microamp source in parallel with a 4.25 mega ohm resistor. Let me move that over so I'll have much more room. 4.25 mega ohm. Now I'm converting the practical voltage source in purple into a practical current source. So that's 15 volts divided by 1.2 mega ohms gives me 12.5 microamps. 0.2 mega ohm. Here's my 7 milliohm resistor. All right, so what can I do now?
You can combine the current sources?
Yes, I can combine the current sources because they are connected in parallel. And I can also combine all three of those resistors, right? So what I'll be left with is 12.5 plus 4.765, 17.265 microamps. Now I'm going to combine those three resistors in parallel. So that is 1 over 4.25 plus 1 over 1.2 plus 1 over 7 to the minus 1 power. And this becomes an 825.433 kilo ohm resistor, if my math is correct. So how do we determine the power? A maximum power that could be transferred to our load resistor.
You can change the you can change it back to a voltage, and then calculate it by using the derived equation to figure out the maximum power.
We could do that. I'm going to do a slightly different route. I'm going to leave it as a practical current source, and we're going to derive another equation that'll work for practical current sources. So if I have some current IS, some RS, like so, here's IL, here's VL, right? So we know that maximum power transfer occurs when RL is equal to RS for when it's connected to a practical voltage source. And because a practical voltage source is electrically equivalent to a practical current source, the same condition must apply here. So if RL is exactly equal to RS, then IL is equal to IS over 2, because the current's going to split evenly between the internal resistance of the practical current source and the load resistance, where RL is equal to RS. Is everybody okay with that?
Yes, sir.
So the power absorbed by that resistor RL then is simply going to be the current flowing through the resistor squared times the resistor value. So from this, we can see that the maximum power is going to be 1/4 IS squared RS. So for our voltage source, we had P max is equal to Vs squared over 4 Rs, right? So we still have that same factor of 1/4, but now we just have, instead of having the power relationship for a resistor, which is V squared over R, we have the power relationship for a resistor with a current, I squared times R. So from that, Max is 1/4 times 17.265 microamps squared times 825.433 kiloamps, or excuse me, kilo ohms. Two five times sorry. X squared times 615 point, no, excuse me, 61.509 microwatts. Let's check. Yep, so a little bit of rounding error for me not storing values in my calculator, but we're within less than 1%, so it sounds good to me. All right, so hopefully this practical voltage source, practical current source, source transformation stuff is fairly straightforward. Any other questions on it before I talk about what we're going to be coming up next?
I have one question. So
Yeah.
how did you figure to have the RL equal to the RS resistor to get the maximum value?
Let's see. I'm not sure if I went over it in my lecture or not. So let me open up a new thing real quick here. File, open. All right, so do you mean in general or specifically for the current source?
Just like in this specific case.
Okay, so let's say that we have a practical current source. All right, so in the general case where RS and RL are not equal, we can find the current IL using current division, where we will have IS multiplied by 1 divided by RL divided by 1 over RS plus 1 over RL, which algebraically simplifies to IS multiplied by RS over RL plus RS. The power absorbed by that resistor RL is then going to be IL squared times RL, which is going to be IS squared times RS over RL plus RS squared times RL. So let's do some math here. IS squared RS squared RL divided by RL squared plus twice RL RS plus RS squared, where I just FOILed out that denominator, pre-algebra style. And let's see. I'm trying to think. So I know that I'm going to be taking the derivative of the power with respect to RS, I believe. Let me look at my notes real quick here. Since it's been a long time since I had to do this by hand. All right. So whatever RL. So that should be. Yeah, that's all right. Trying to remember if I take the derivative with respect to RL or RS. Looks like I take the derivative with respect to RL. So the derivative of the power with respect to RL, and I need it to equal 0. All right, so this is going to be ugly. How can I do this easily? Let's see. So quotient rule, right? Since we have a function f of x on the top and a function g of x on the bottom. So where, let's see, f of RL is is squared RS squared RL, and G of RL is RL squared plus twice RL RS plus RS squared. So the quotient rule says that we take the G term, RL squared plus twice RL RS plus RS squared times the derivative of the F term, so that's going to be IS squared RS squared minus F of RL, so that's IS squared RL times the derivative of G of RL. So that's going to be twice RL plus twice RL. So let's just write that as 4RL. No, that's not right. Twice RL plus twice RS. Divided by G of X squared. So that's going to be RS plus RL to the fourth power. Okay. We want this thing to be equal to 0, which means our numerator needs to be equal to 0, right? That's what we're concerned with. So we have RL squared plus twice RL RS squared times IS squared RS squared minus IS squared RS squared RL twice RL plus twice RS is equal to 0. There's a common, well, let's multiply this stuff through. No, we don't need to do that. So there's a common factor of IS squared in both terms that we can get rid of pretty easily. There's a common factor of RS squared in both terms that we can get rid of easily. So this is going to leave us with RL squared plus twice RL RS squared minus twice RL squared plus twice RL RS is equal to 0. Let me double check my algebra here. So RL squared hold on. Sorry, I made a couple of mistakes here that I'm going to have to fix. Better. This way. Oh, goodness gracious. All right, so let's try this again, but not making dumb mistakes. So RL squared plus twice RL RS plus RS squared times IS squared RS squared minus IS squared RS RL twice RL plus twice RS is equal to 0. So we still have that common factor of IS squared that we can get rid of. We still have a common factor of RS squared that we can get rid of. So we have RL squared plus twice RL RS plus RS squared minus twice RL squared, because that's that RL times 2RL, minus twice RL RS is equal to 0. There we go. So we have a plus 2 RLRS and a minus 2 RLRS. So this leaves us with RL squared plus RS squared minus twice RL squared is equal to 0. So let's see, so that's negative RL squared plus RS squared is equal to 0, which means RL squared is equal to RS squared, or RL is equal to RS. So that's why when we have a practical concurrent source, mathematically why when we have a practical concurrent source, maximum power transfer occurs when RL is equal to RS. Or again, we could have used the explanation that I gave earlier. Since the practical current source is electrically equivalent to the practical voltage source, if RL is equal to RS is the condition under which a practical voltage source applies maximum power, then RL equals RS must be the condition under which a practical current source applies maximum power also.
Thank you. That I wasn't expecting all that. Thank you.
Yeah, no, it's I may have glossed over things in the lecture because I didn't want to have to do all this.
I understand, but thank you. It really does help a lot.
Okay, well, you're welcome. Any other questions?
Yeah, yesterday I was working on homework 7, problem 3,
Homework 7, problem 3. Alrighty.
and maybe I'm just overlooking something simple, but I couldn't figure out how to relate Vx to anything else in terms of the dependent voltage source on the far right.
Okay, so let me add another sheet of paper here real quick. Edit, document insert. All right, so homework 7, problem 3. Alrighty, may I ask which mesh current, which mesh did you label as I1 and I2, etc.?
I1 was this bottom left corner, the small one on the left.
All right, so we're going to call this IA. I don't want to use I1 because there's already
Yeah.
I1 in the problem statement.
IB was the one next to it, and then IC was the large one.
Alrighty, and you are saying that you need to figure out how to express Vx in terms of your mesh currents, right?
Yeah, wait, could I just do KVL around that on loop right there, IA?
You could. So if we start in the bottom left-hand corner, and I'm going to call this guy V25 with this polarity, we would have V1 plus V25 minus Vx is equal to 0. And that means that V1, which is given to you, plus 25 ohms times IA minus IC is equal to Vx.
Yeah, okay. That's all I needed.
Yep. You could have also done it around the mesh B,
Yeah.
where you would have, let's call this V20 and V100. And so you would have Vx is equal to, actually, let's change the polarities of those guys so that we don't have a whole bunch of negative signs. Minus, plus, plus, minus. All right. 100 IC minus IB plus 20 IC minus IB. So that's one way to do it. This is another way to do it, and they'll both give you the same answer.
Alrighty, thank you.
Any other questions on any of the homework problems or anything? All right, well, what we are going to be doing next is what's called so actually, let me pause that real quick. The topic that we covered today, source transformations and maximum power transfer theorem, is the last bit of material that is on exam 1. So we have 2 lectures, one on, today's Tuesday, right? Yeah, so one on Thursday on Thevenin and Norton circuits without dependent sources, and then one on next Monday on Thevenin and Norton equivalent circuits with dependent sources. Now, you guys haven't looked at this stuff yet, probably, but Thevenin and Norton equivalent circuits are simply another way to turn things into practical voltage sources and practical current sources, respectively. But it will work even if you can't do simple source transformation techniques. So while Thevenin and Norton equivalent circuits aren't technically on exam 1, the stuff that we learn in those 2 lectures can absolutely be applied to the exam problems to effectively work it in an alternative way that may be slightly easier, just depending on the circuit that I give you. So the material that we're about to cover isn't on exam 1, but it can be used to make exam 1 potentially easier. So anyway, all right, any other questions or anything? All right, nobody's saying much of anything, so I'll see you guys Thursday morning, and I'll try to get both yesterday's Zoom meeting and today's Zoom meeting uploaded to YouTube today. So thank you guys, and I will catch you Thursday.
Thank you, Dr. Hartman.
Have a good
Thank you.